Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with LearnBay.co. Happy learning!
We'll go through it in details. So now the point is that we have exploration and exploitation. Very, very important. What is exploration and what is exploitation? The entire reinforcement learning is based on these two concepts. Okay, so now what I know is you have for example, the agent can explore new paths. Okay, it can find new information from the environment and try actions that were not tried before. Okay, that is exploration. And exploitation is agent memorizes the one path and never tries to explore a new path, utilizes known information to maximize the reward and try previously well reward action to receive the big reward. So in real life, what is exploration and what is exploitation? So for example, you are working in Java. Maybe you are a web developer. Okay. So you passed your engineering in 2008. You then joined any company like Cognizant, TCS or something like that, and you are working as a Java developer. Okay. So you are working for last 10 years. Okay. Now you are good at that. Okay. So you are like you started with a Java developer, and right now you are a solution architect, and you know about all those web patterns and everything. You are in on-site preferably. Now you have two paths. Okay. Now after 8 or 10 years of industry, you can no, now you are in offshore preferably. Just you are working in Bangalore or Hyderabad for around 7 years. Now your company or your boss tells you that you have the option to go to on-site. Okay, based on your skill, and you will can like you can stay there and stay with the client, and it's a long-term on-site opportunities. Right. This is exploitation. So based on your skills, you have a reward. Reward is your salary, and you will take a path. So maybe you wanted to become a principal architect and move on site and earn more money, get more into technical era. Now the next question is exploration. So what is exploration? Your mind tells you that no, I have been in that Java field for a long time. So as the technology has changed, either I wanted to move up into a new technology. Okay, so you think data science is a very good thing to start off because it has a higher demand. It has a very a good demand in the market, and I wanted to explore that. Okay, but there is a risk associated with that because you do not know what will be the outcome, right? But you are listening from the friends and all that. It's a very lucrative field. Second option can be you wanted to decide to go for an MBA for any business school, right? So you know that the salary and all after MBA is pretty good, right? So now there is a dilemma between exploitation and exploration, whether you will go to on-site or whether you take a new domain and try to explore that, or a new kind of a skills or a new education like MBA or MS you wanted to bring in. The rewards are not clear for exploration. You know, you wanted to explore, right? It might happen that it might not work for you, but still you wanted to explore. So machines also have this habit, like this type of dilemma, whether to exploit based on your previous learning, or it might wanted to explore. And this is the entire like a gamut of problem that any reinforcement learning is trying to solve. We'll see how it is able to solve. It is not like humans that like we also have some tangible points, right? So we do a cost benefit analysis. We ask our friends. We do attend a kind of a webinar, read books, consult with seniors, and then we take a decision. Still, we are not sure whether whatever decision, if we exploit, after 2 years you are in on-site and you feel that the work that you're doing is crap, right? And you are fed up because you are working in a Java for a long time. You wanted to explore. If you wanted to explore, go into a data science course, you do not get a job, for example, or internship, or you are still working in the same domain, you are not able to shift, then you are a fix that whether my old like the technology was good or bad. So this is a real life stuffs, and you have to understand that. So this is a difference between exploration and exploitation. Now, so this is a reinforcement learning problem. So again, I will try to explain it. So you have a rabbit and you have an infinite carrot. Okay, plus one each. So this is an infinite carrot. Okay. Now at the top right corner of the maze, there is a bunch of carrots. 10 carrots are there. Okay. Now, the focus of the reward agent, the focus is on the reward. Agent will never reach the bunch of the carrots, okay? Because there is the electric shock here. Agent have to explore the nearest source of reward, even if the source is small. Okay, so it is a exploitation. Okay, so it will what? It will go to the nearest cells and get 111. So its total reward is 3. Now, whether the agent will stop here or it is fascinated by high rewards, and this is what? This is exploitation. It is based on why it is exploitation, because it moves up, it gets a reward, it's very happy, it wanted to maximize it, it goes left, it again gets a reward, it wanted to maximize it, it goes left and it gets a reward, it wanted to maximize it, so it gets 3. It cannot go left, it cannot go left, it cannot go right, it cannot go bottom, so it's stuck here. It's happy. I am happy with my life. I have done a good amount of Java programming. I am sitting in San Francisco Bay Area. Okay, I am happy. Every day I'm going to office, working. There is no tension and all. I am very happy. Now there is another decision. Is that I have heard from somebody that this salary that I am getting is around preferably $80,000. I heard from a friend that a data science pays me 150K. Okay. Now, whether I need to explore, I go up, I go left, and I go up. This is a good part. I go here, I get an electric shock because I apply for some companies, I do a kind of a course. People are not ready to take me because I don't have experience, or I'm not able to crack the interviews. These are the life events. Okay. There might be a recession and all, right? Or there might be like I'm not getting a job because there are too much of people who are doing data science, right? So now the robots is also this. So whether so this is a kind of a exploration, or this is kind of an exploitation. So we'll see how the robot is able to decide on both of them. Is it clear? Or any questions is here? This is a very important concept. Clear, right?
Yeah, so the nearest ones are exploitation, and the ones which are far away is what you're saying is exploitation.
Yeah, so it is just nothing but I am getting one reward and I'm very happy. So I wanted to maximize the rewards that are nearby me. Explore is there are huge rewards, high rewards, but I have to explore to the other grades. So I have to explore. That is that is exploration. So we have to decide between exploration and exploitation, and I gave you the real example. Now there are some fundamental ways how to do it. So that
when exploration will end after exploring everything, correct?
That depends on you, right? I am a guy who is happy with 3 carrots. Okay, you
no,
are.
For example, if here 1 carrot is there, means far distance. If 1 more carrot is there, so if I get that carrot, then also it will be exploitation because 1 more is pending, correct?
So here you are getting 1 carrot. So this is also we are exploitation because 1 carrot we got here. Now we move up. Okay, so you are doing a kind of a exploitation. Then you get another carrot. You are going here. Okay, you get another carrot. So you are going here. You get another carrot. You get here and you get here. This is not a exploration at all. This is exploitation. Exploration happens when you do not have any rewards in between. So you go here without thinking of a far reward. So a reward might come after maybe 1 year. So you are doing a data science course. Do you expect a result to happen tomorrow? No. Happen after 1 year, right? You are doing exploration. You believe that a high reward will come, but for that you have to spend enough effort. So these are the efforts he's spending. Either the effort you are doing with time, you're investing your time, you're investing your knowledge, right? You are spending 3 hours per day for that, right? You're not getting immediate rewards, but you hope that there will be good rewards that are coming maybe after 2 years, right? So this is kind of a
Okay.
exploration.
Okay. Without reward, action is exploration.
Yeah, but you know reward, but some reward is there. You know this one is there.
Yeah, yeah.
I'm not
In
seeing
the
it
long,
long.
long.
Yeah. Okay. From here, this I will teach you later on, maybe a better way. Don't think of this. We will go through it. What is policy prediction and policy control? We will go through it. So this is a framework for example, this might be a very, very good way. Somebody gives you a problem, okay, and it tells you to frame it in a reinforcement learning way. So a learner to ride a bicycle. So problem statement, interviewer might ask you that a problem statement is tell a robot to learn a bicycle. So how it will able to learn? So learner is the agent. This is a framework for any reinforcement learning. So some business problem is given, how you frame it out. Learner is the agent. Nature is the environment. Environment is nothing but a road. Okay. Position of bicycle, surrounding vehicles, pedestrian, crossroads are states of the environment. So there can be multiple states for that environment. Okay, so environment is a road. There can be multiple states, right? So position of the bicycle, position of opposite bicycle, carts, pedestrian, crossroads are nothing but states. Turn left, turn right, keep straight is the actions I am taking, and I am getting a rewards. Now reward can be a cumulative reward or it can be a discounted rewards. If you have this type of you define the problem in this way, now you can solve it through a reinforcement learning problem. What I will do, I will write a what I will write a hidden Markov model for that. Simple. So you define a grid like this way. Your cycle starts from there. This is a starting position. This is a end position. So starting position is a gate from your home gate, or you can take it to be home. And this is the exit or end point is your neighbor's home. Okay. Neighbor's home. And this state you define as A. Then you move up to B. Then you move up to C and move up to D. D is the end. Okay, so this is the so this is our environment, right? Learner is that bicycle guy, the agent who is starting from here. Now you then define the state. So you move up and then you define the Markov's model. So A, then B, then C, and then D. Yesterday we saw it. Then you can define the transition probabilities, as well as then you can define the value function, define the reward. So your actions are, again, I told you, right, how to do it. So you can define your actions like this way. Actions are what? Left, right, down and up actions. Your states are nothing but the 4 state you have it, A, B, C, D. Okay, here the states are, for example, this is your home and this is your neighbor's home, and you divide it into 4 episodes, 1, 2, 3, 4. So it is you go to your gate. You go to some pawn shop that is after your gate. you go to grocery shop, that is after your gate, and then you go to neighbor's house. So you can divide into episodes, and you can define this to be A, this to be B, this to be C, and maybe you can remove this.
So A to B is just one episode, is it? And B to C is another episode.
Yeah, so A to so what you divide is that A to D, you can define it to be a big chunk of maybe 10 minutes. Okay, so
Okay.
by 10 by 4 is 2.5 minutes, one episode. And
Got
for
it.
one episode, what will happen? These type of so for one so this value table would be iterated for this episode. So 4 episodes, 4 times it will be iterated. You remember, right? 4 times it will be iterated, and what will happen is that episode 1, episode 0, episode or episode, you can think of episode 0. Your all the values of A, B, C, D will be zero, 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 zero. Episode 1. Now you are saying after 2.5 minutes, what is the result? So 0.2, 0.3, 0.4, and again 0.6. Second episode, third episode. So ultimately, after you complete, so you will fill up that value table. And then from there, you will decide that which policy is greater, right? So now you decide that if I move from here to here and here, this is one policy. So this is my optimal path. And I divide it into episodes. So episodes, one episode complete means a time gap. So maybe you can think of this to be a time gap. So 2.5 minutes, you are seeing that value table. Here it is 5 minutes, then it will be 7.5 minutes, and there will be 10 minutes. So now you take each of the iterations, your value will change based on the hidden Markov model. And then it will be kind of a states. States are your A, B, C, D, right? The states are A, B, C, and D. And here you can define that to be the states. You will define it. Maybe you are saying that maybe based on the kilometer you have driven, right? So these are the 4 states. So here to here, you can. So these are episodes: E1, E2, E3, and E4. 4 episodes, and for each episodes you have that time small state. So these are the ABCD states here. So it might be that and that will depend on the surrounding vehicles, and you define the states based on that. So it might happen that preferably so these can be states also. So preferably you know that so for example okay, there is a problem. I will explain. This is not correct actually. So when you are moving from start to end, these are your points A, B, C, and D. Okay, so these are points that you're moving. So A, this is B, this is C, and this is D. So these are actually time. So you can think of that to be 1.5 minutes, 2.5 minutes, 5 minutes, 7.5, and 10. Okay. Episodes are nothing but, now what you do is you train your robots. So episodes are nothing but you have a in deep learning, there is a concept known as batch size, a batch and number of epochs. Episodes are epochs. So episodes are when you try to run a robot, for example, you will not have one iterations of this, right? You will have 10,000s of iterations. So these one iteration is how many times you train your robot. So this is one episode. Again, you train your robot. This is another episode. Third episode is third time, because you have to take the observation, right? Now, based on 10,000 episodes, you will decide that whether it will be moving from this, A, B, C, D, or it might move from A to B, whether it move from this to this, or will move from this to this. I understood the episodes are the trials. So you will, so this is what this is, the episodes are consist of states. How many times you will train the robot before your value function is not improving. So you are saying maybe after 10,000 iterations, my last value of ABCD is not improving. So ABCD is how much? 0.10. You started with 0, right? So at episode number 1, it was 0. Everything is 0. I initialized. 0.2, 0.3, and 0.5. 10,000. 10,001. The value of episodes, the value are not improving at all. So I cannot do it infinitely. Then I don't have resources. Right? So it is 0.11, 0.211, 0.311, 0.51. Very, very less. There is a delta change. So the delta change, between episode 100, 10,001 minus episode 10,000 is very, very close to 0. That means there is no change is happening. Delta change is 0. So I think I could stop. Now the value you get it from here will decide whether, so I will show you. So now you will see, you will have states, right? So you will move from state 1 to state 2. Okay. You have the transition probabilities. So I'm after transition probability. So I'm not interested in transition probability, for example. I have calculated the value. So you have that value function right now. So value function is 0.4 after A2, then you do A2. So all the combination you do A to C. Value function is 3. A to D, the value function is 0.2. Okay, then you do B to C. Value function is 0.1. B to C, right? Then your value function is B to D is 0.3. Then your value function from C to D is 0.2. So now you decide A, B, A, C, A, D. So your value is which is greater, so 0.4. So you will move from A to B. Then from B to, then you see B to C is 0.1, B to C is 0.D. Then you take B to D. All right. Then I move up into the D state. So your path will be A, B, C, and D. So you move from A to B, and then
B to D you can
B to
move. So
D. B to D.
okay. So A
you
to
could
B
have
is
taken.
so A to B is highest. Then I move up into B to C is okay. So B to C I have I could have many values. So B to C is 0.1 and B to D is 0.3. Then I take B to D. So A to B and then I take B to D. I am not going into C at all. Okay. So this is the optimal path. So in this way, it is able to calculate because B2C and B2D, but B2D is higher than B2C. So I will not take B2C. This cancels. So B2D. So from A to B, I go directly to B.
So now after you reach to C, now C for CD also there is one value is there. So you will not move because
No, I will not take
already
because
you moved because of that.
B2D. Yeah. So this is the way you can then at least somebody tells you you can define the reinforcement learning, do that transition probability, and you can explain it into the guide. Okay, so that I expect you to do for most of the problems, simple problems at least. So this is our conceptual understanding of a reinforcement learning, and then we will go into the open gym, but I will show you one example of an open gym, but only problem is that I work in collab. Okay. So OpenGym doesn't, sometimes there is a problem with rendering and all. So I will just show you one example, but the problem is that you have to do that example on your Jupyter notebook. So it is not on Google Colab. So if you can do it, that is better. Just I will show you one little bit of example how you can code it in OpenGym. Okay, just hold in for a minute before we move up into the next topic.
The same we can try in our Jupyter notebooks,
Yeah,
right?
yeah. Jupyter notebook you can try because I use Colab. So there is some
Okay.
problem in the Colab, but I will show you of the codes.
And how is this different from the Kalman filters and all that they use for time series?
That is completely different. This is OpenGym is kind of a, this is from
No,
OpenAI.
I'm asking reinforcement learning. How is Kalman filters and hidden Markov models different?
See, hidden Markov, so you saw that, right? So we are using a hidden Markov model to find out the transition probability and then find out the policy. So through hidden
Correct.
Markov model, you can do a reinforcement learning, right? And
Hmm.
regarding Kalman filter is, I think it is based on Bayesian, right? So the Kalman filter is completely based on like Bayesian learning. So you have still some data, right?
Hmm.
So
Okay.
yeah, in Kalman filter, you do not have sufficient data, but you have some data and you are trying to replicate the environment based on that.
Correct. Correct. Huh.
Here, there is no data at all. So you start with no data. So how will you proceed? So that's a
Okay.
different. Okay, so I will go to this OpenGym and see whether yeah, this actually have some problem. I will just in Colab if I face some problem, but so I will just explain you a bit of code here, very simple, and I will share the codes with you. Okay. So this is so in OpenGym is a environment where we do a reinforcement learning. Okay, and OpenGym is a part of OpenAI. Okay, so and you have to download. You can have to pip install the gym. So what I do is that first of all, these libraries are constant. And these are standard. So IP widget and IPython display is used for like for example to use a button and all, right? So here you have to import gym. So if the gym is not there, so what you can do is that you can do a pip install. So it is there. I have already installed it. So you have to install it the gym and then I import the gym. Yeah, it is showing error because I have not installed the JS animation. So I define a helper functions here. So what I do is that I have, so these are the clicks and display buttons. So for example, when I click, I will show you what it does. So these are nothing but the buttons I am creating. So you can create the buttons on this thing. So when I handle right display, handle left button, when I click it, what actions it will do. Okay. So here there are certain libraries that needs to be installed for the gym. So these are the OpenGL and anything. I am facing problem in Colab, so but I will show you the output of this thing. So you can go to Yeah, I can go to this website and I will just paste it for. Yes. So gym.openai, and you can see a lot of environment is already defined with this. So what we do is that when you import gym has different environment. So for example, carpool. Okay, so carpool is nothing but, so if you wanted to view the documentations or wanted to view the GitHub code, you can go there. So so this is the official documentation of gym. You have to pip install gym and or git clone gym, and then you can import the carpool. So when I say import gym make carpool.version1. So carpool is what? Carpool is you are trying to balance the pole here. So what will happen is that it will slide down in the left hand side. It is automatically with reinforcement learning. You can just like you can just keep the carpool from falling. So I will just show you up this thing. Actually, the problem is here. I'm not able to render this. This is a problem. PLT is not defined. This is the carpool. So I wanted to balance it. Okay. So when you have left, you have this coordinates. So it will give you the coordinate of this button, okay, for testing. So there is a problem with this thing, because if you run it in run it in your for example local machine, it will work. So what will happen is that it is kind of a this thing what we are doing. So yeah, it is you are able to see when it is going into the left, it is able to like it is able to come back also. So for example, yeah, so you wanted to balance it, so you can, yeah, so you are able to balance it. There are different environment and spaces that you are able to balance it. So you can just so for in gym there are a lot of environments. So for example, carpool is one of the environment. Then you have, for example, you can play an Atari game and everything. So you can just search. So you can just help use the pendulum to just do this thing. So there is a code for that, or you can just help, you can play with this also. So the yeah, so what will happen is that the computer will play. So it will automatically play and try to win the game. Okay. So these are actually applications. So we'll be not be interested in that. We wanted to know how the internal like how the internally this thing is working. So if you wanted to do it, you can just view the source code and just write the code inside it. So everything is very simple. So you have that code and all. So you can just code it around, and you will be able to see that what is there in the OpenGym. So I will not go through it in a detailed way, because I will have another sets of algorithms that I wanted to cover. So is it okay?
Yeah, sure.
Because this gym is very easy, so you can just explore among yourself that what is there and all. Okay. Okay, so right now we will move into a deeper concepts from here. So we will understand what is policy, what is value. Okay. So what we have understood. So reinforcement learning is nothing but an agent is there. It is interacting with the environment. When it is interacting with the environment, it is getting a state. Okay. This state is there. We saw it. From state, the agent does some actions interacting with the environment. Okay. Environment gives him a reward. So this is the entire functionalities, right? So environment, when agent is interacting with the environment, it gets a state. Okay, when the bicycle is running on the road, there are certain states that can be based on the time. Then the agent performs some actions, whether he wanted to go this way, he wanted to go this way. These are the actions. He wanted to go this way. This is start and this is end. So these are actions. So what are the states? So if the environment is this, and this is your home, this is your neighbor's home. Okay. Now you divide it into 3 states based on time or based on location. Maybe your front gate is one state. Front gate to your grocery shop might be a state. Grocery shop to neighbor's gate, a neighbor's front gate might be a step. And here is the total gate of the neighbor. So you can divide it, depends on the state, or it can be time also. So you have starting point, end point, 10 minutes, you divide it into 2.5, 2.5, 5, 7.5 and 10. So that can be also vested. Okay, so he does the actions. So actions you have understood and get some rewards. Again, the rewards can be 2. If he falls down, it is -1. For each of the steps, it can be +1. If he just doesn't paddle, he just stays in the bicycle, it gets 0. He's not moving at all. In the last step, maybe final step, when he moves from your grocery shop to the neighbors, he can get +3, more rewards, so that he have incentives to move faster. Okay. So in this way, I can define the rewards. Clear? So that this you have already been learned. Okay. Now, what I am saying is that simple. Environment is there. So it starts with this environment. So it starts with state 1, what we talked about. It gets action 0 and a reward R1. So it starts with S0, A0. It's the initial value of initial value, right? Now what is it does is that it moves up into this. Okay. Now it does some after S0 and A1, it moves up into from state S0 to state S1. Here S1, he does some action 1, he does a reward, gets a reward R. Okay, so it can be the next landmark. So S0 can be your home gate, S1 can be your maybe S1 what we talked about. So it's a home gate. Home gate, it can be your front gate. Okay. Now it move up into after the action it moves into R2, S2 and S2. So it is nothing but if you have this stage, this is your house, it is neighbor's house. You define the state as define the state. Maybe this is front gate, grocery shop, front gate of neighbors, home gate of neighbor. So it starts with S0, A0. Next, it moves into S1, A1 and get a reward 1 again. It can be S2, A2, reward 2. It can be S3, A3, reward 3. And here is S4. I'm not doing any actions here. and it doesn't have anything. So it is just a S4, and there is no actions here. Okay, so
I think this R1 is a reward for S0, A0, correct?
yeah. So when you do from S0, A0, you do some actions and get a reward here. So R1 is here, R2 is here, R3 is here, and R4 is here. So you can define this to be S4, R4 also. So what is this? So this is S4, A4, R4. Here you are doing R4. So in this way, there can be several steps. Now this is a problem. So in a simple environment, see, there are around a lot of actions to take. So this would be huge, right? So this is the goal of the agent. So S0, A0, R1, S1, A1, R2, S2, A2, R3, S3, A3, R4. Max. So what is the goal? What is the goal? Our goal is to maximize the entire thing. Maximize the cumulative rewards. So this is our main goal. Okay. Now, yeah. So right now I will touch upon two things. It can be a episodic task. Okay, so episodic tasks are the same thing. You wanted to move your bicycles from your house to neighbor's house, or you are playing a game. Okay. Episodes are, what is episodic task? It has some end state. You're training a robot, or you're providing a self-driven car, right? So this is the episodic task. Continuous task is, for example, share market. I don't have any outcome, right? I wanted to maximize my rewards, but whether there is an end to it or not, I do not know, because rewards can be anything, right? I wanted to maximize it because tomorrow's reward can be more than today's reward, right? Because the share market might increase, or yes, tomorrow's reward can be less also. So for example, you wanted to write a reinforcement learning code to maximize your returns from the share market. So that should be continuous task. An episodic task is you are training a robot to move from your house to neighbor's house is an episodic task. Clear? So then why I described it is that your reward function will depend on whether it's episodic or continuous task. Okay. Continuous task we will not touch upon because it's a very, very complex thing, and there is DQN and other things there. So that is, we are mostly interested in episodic tasks. Okay. Maybe a separate treatment needs to be done for continuous tasks. Maybe we have to take a separate session on DQN and everything. So that's a deep reinforcement learning. So that's unless if you do not have a foundation of episodic tasks, you cannot do a continuous task. So goal of the agents are there. So I wanted to train a robot to move from your house to your neighbor's house. What are the states? The position and velocity of the joints, measurement of the ground, and contact sensor data. These are the states of the robot. Actions is what force applied to the joints. Or action. So you give him the velocity, you give him the measurement of the ground and context sensor data. So these are states, are nothing but the inputs. Very, very crude way we are explaining. But inputs, there is a difference. I'm not calling it to be an input. There is a subtle difference between input and state. Actually, state is nothing but an input. But input, what we think about is a predefined thing. Okay. So input means a file. Okay. But this state is an input that an agent gets from the environment through automatically through interacting with the environment. Nothing is but IoT data. You fix a camera in front of a robot. What it does is that it through image recognitions, it scans the entire environment and find out that what are the so if there is road is flat or it is like it is slanting, whether any people is in front of you or not. Okay, or we need a IoT data to when the robot runs or walk, it is able to calculate the position or velocity. Okay, so these are inputs, but the agent decides on that. So we are not feeding anything explicitly to the agent. Then based on the state, agent takes action, that is the force applied to the joints. What means if the force applied to the joints means it is able to run or walk. Okay. And the reward, what is the reward? Reward is whether if the agent falls down, we can give it to be -1. If the agent runs completes his task, it can be +1, and that reward can also be discounted or a normal average, right? We will see it. And also if the agent doesn't run, it can be 0. So this is a new, we have defined everything. Now see how complicated a reward function is. So next we go into the reward function. See the reward function. We have defined it. This is a main problem of reinforcement learning. You require a scientist or somebody to define, or a physicist to define the reward function for you. So can we see reward functions in a little bit of so it works fast. Okay. So minimum of Vx plus Vx max. So I am taking a proportion to the robot's velocity. So Vx or Vx max, I am taking a, just hold on for a minute. Can we take a break of around 10 minutes? Can we take a break before, because it requires a little bit of concentration, and can we take a break of around 10 minutes right now, and then
sure. Yeah.
Okay, just a break of 10 minutes.
Yeah.
Start the it should be 10 minutes. should we start? Is everybody back? Or wait for a few minutes?
Yeah, we can start.
Yeah. So see, reward function, I want to take time to explain the reward functions for a robot. See, this is a real reward function. So what it is doing, the first is that minimum of Vx plus Vx max. That means Vx can be the speed at which he is walking. Okay, and Vx max might be he is running. So I will take a minimum of that. Why I am taking a minimum of that? Can anybody, what is intuition? I want not my robots to run at least, because what will happen if they run, they have a higher probability to fall. I have defined the reward function in such a way that I will give more emphasis to walking rather than running. Okay, so I'm trying to control it. Okay. The second is the reward function. What is 0.05 of Vy square plus Vz square. So what is that? It penalizes the deviation from the forward direction. So what I am doing is, what is this? So you have what? You have, so this is what? Vx and Vy. So when I am doing a Vx plus Vy square, it's a kind of a Pythagoras theorem, right? Vx square plus Vy square. So what it means, right? This is a Pythagoras theorem. Vy square plus Vx square. So I want my robots to run in a linear fashion. Right? I don't want, it's a linear function, right? Vx plus Vy square. If it is curve or it is this one, so it should be polynomial, so it should be increasing, right? So this is a intuition that I want my robots to learn in a straight line rather than zigzag line. Good. Then what we are doing is we are then what it does is that it is u square. Okay. Next is 0.05 into y square. So y square is something that I use it to penalize the deviation from the center of the track. So if it moves in a sideways, then it penalizes it. So see, the coefficient is negative. Negative means I am penalizing. Positive is I am getting a positive type of a thing. So it's a positive actions. So negative then is negative 0.02 u square is what? Penalizes torque. So it is too much of torque, it might fall, right? It might, if it doesn't move in a straight line, it might fall. If it is moves too fast, it might fall. If it deviates from the center of the track, it might fall. So these are negative, right? And the last one is walk as long as possible. This is a time factor. So it's a constant reward for not falling. So it is not dependent on anything. So I am saying that if it is runs for around 2 minutes or 3 minutes without falling, so this is a kind of a reward I am getting. So see, so some of the parts of the equation helps to robot to walk forward. Something that I am using to okay, here minimum of Vx plus Vx max is something that I am using proportional to the robot's velocity. So what I am doing is that it is a plus function. Sorry, I thought it to be negative. So plus function means I want my robot to run. So the more the velocity is, this function will be more. That means your reward function is more. So I wanted to robot to walk fast. It moves in a straight line. It moves without deviations, with a minimum torque as long as possible. So this is a real world reward function. See, so much of now you have to maximize the reward function based on these factors. Now you define the states are input. So this is so you have to then think of the entire environment and come up with the reward function. That is why defining a reward function is very, very tough. Okay, so this is our generic function. See, R1 plus R2 plus R3, but the intuitions you have understood, right? Any questions in this?
We can use GPS coordinates also if we are training something robots or something like this, right?
Yeah, so your velocity and your positioning that walk forward will come from your GPS. For example, GPS, no, you have the camera, right? It will able to locate the coordinate and pass it. So everything that is coming from either is coming from the sensor or it is coming from the
Coordinate.
so, yeah, so it sees the environment and pass it. So this is a reward function actually, real life reward function.
So we can tell like if these coordinates are there, then reward. Yeah. Otherwise, negative reward. Okay.
Yeah. So this is the see, it is still naive. So in a real life robots, so many of the things needs to be added. So that's why reinforcement learning is very, very tough. And we wanted to give, and this is also dependent on time. So it should be, I told you, right? We have to divide it into time and then add it, the temporals things. So we can just add it or we can have a discounted thing. So this is a discounted. So so it can be RT plus 1, lambda RT plus 2, lambda square RT plus 3, and lambda 4 RT plus 4. What it means, intuition. Intuition is that if the lambda is 1, that means what? That means you are giving each of this time step, you are giving equal importance. Simple. Lambda equal to 1 means what? It should be sum total of your all the rewards. Okay, that means you are giving equal importance to each of these rewards. But in real life, when you give equal to lambda equal to 0, what will happen? You are putting all the importance to your recent steps rather than previous step. So when the lambda's value is less, you are putting more importance to your recent rewards rather than previous rewards. We saw it, lambda equal to 0, gt equal to rt plus 1. That means you are putting more emphasis on the recent reward. If the lambda is more, that means so lambda equal to 0, right? If the lambda is more, so 0.5, what will happen? You are putting your rewards also are dependent on your previous rewards. Is it clear? So if lambda equal to 0, that means what? Everything becomes 0. So it is RT plus 1, right? So what is RT plus 1 here? RT plus 1 is nothing but your just a reward that is RT plus 1. So that is the recent rewards. That is more important. So that is lambda equal to 0. If lambda, so now you can define lambda to be 0.5 also. So for 0.5 is it will take some of the rewards from the other steps. So now you have to define, right, that this is discounted, that whether you wanted to give emphasis on the rewards for each of the steps, or you wanted to give more emphasis to the recent rewards rather than previous rewards. But in real life, I told you, right, your actions are more dependent on what your rewards are more dependent on actions you take today or tomorrow or previous month rather than what you took last 3 years. So I want so the reward function should be always be discounted rather than giving equal importance to all the steps. So but it depends, but still I feel that the rewards should be discounted and your recent rewards should be getting more importance rather than previous rewards. Is it clear?
Yeah.
Okay. So so these are the actions. So again, we are discussing the actions. Actions can be, so I will define a, sorry, I will define a, I will define a problem where, for example, a docking machine is there. Okay, so docking machine collects the garbage. This robot collects the garbage and it goes into inside docking machine to dump the garbage. And there is a charge also. So when it sees that it has less charge, it comes to the docking station to get the charge. Okay. So now it will depend. So how much distance it will travel will depend on the charge you have it, right? And when it sees the charge is less, it will go back to the docking station and recharge and then again move. Now, what are the actions? Actions are three. What is search, research, and wait? So it can search. Search means what? It can search in the environment to get more garbage. Recharge is, it will go back to the docking station to get the recharge. And wait is that it will not do anything. There is no garbage, I am waiting. Okay, this is idle. These are actions. What are the states? States can be two states, high and low. High means it has high charge and it has low charge. Now I can define the entire hidden Markov chains with this. So we will explain this in a little bit. So for example, this state is high. That means it has a high charge. Okay. So what it does is that if it is a high charge, it can wait. Okay. So it is waiting. So what is the probability of waiting? Waiting is very less because it is high charge. That means it is going to explore things, right? It is going to explore things, right? Because it is, I have a high charge in my robot. So robot should not wait. We should not idle. So it should go and search in the environment and collect more garbage. The next step is that so the probability of waiting is less. Okay. So what I am doing is that I am trying to map the actions with the states. Okay. So next thing is that if it is high, it will not recharge. Okay. It will not recharge because it has a high. That state will that actions will not happen. When it is high, then it will search. Where it is searching, there can be two things that can happen. One is that its charge remain high. It is not moving too much distance, or it is moving, it has moved a lot of distance. Then its charge becomes low. Okay, so this 40% is a probability. So what is this? I can have to select a different color here. The color is a, so this is what? So this is what? This is the reward. Oh, no. This is a reward. And what is this?
Transition probability.
So from high, you have understood from high. So it gets a reward. It gets a transition probability of 0.7 and a reward of 4. Okay. So this has a lesser reward because if the charge is high, I have no point in waiting, right? Here, what is happening is that it has it has a 70% chance that the charge is high with a reward 4, and it has a 0.3% chance of having a low charge because it has traveled a lot of distance. So these are the rewards and these are transition probability. Now we move up into low. So low, when it is low, it is, I can wait. Okay, so I have some probability of waiting. Okay, why it is 1? Why it is 1 means one means I am saying that when it is low or high, I am waiting. That means I am pretty certain that I am not doing any action. So that's why I have put a transition probability of 1, and I'm putting a less reward because what I'm feeling is that if it is waiting, it is not serving my goal, right? You have to collect more garbage. So if the after the recharge, after I do so the recharge is the state is low, then I do a recharge. What will happen is that it will move up into a high state, but I am not assigning any rewards to it because robot has returned back, right? So when it is doing a recharge, that means it is charge is low. So I have moved or traveled a distance. Then in order to recharge, it has to go back to the docking station, right? So the distance that it has covered, it is become 0. So that's why the reward is 0 here. So I don't want my reward robot to return back, right? Then it will have to again traverse, and for example, the garbage it has collected here, here. But a lot of garbage are here. It is not able to go there. It's again going back to the docking station. So I should negate it. Else it will always go back, and it will not able to collect. It will not able to maximize the number of garbage collected. So function is maximize the garbage collection. Maximize the garbage collection is the function. Okay. So this reward is 0. So here again, when it is low, it is going to search. Okay. So what will happen when it is going to search in low battery? It might run out of the battery, right? So I am giving a very, very negative rewards. So I am saying when your battery is low, you should not do thus any searching. Okay. I am saying is that you should, in that sense, you should again return back to the low state, right? So 0.4 is the reward, and 0.2 means it will again return back to the low state. That means it will not go to the longer distance. So it will just go short, and its charge is there. So it will not run out. So I'm not running out of charge. Because if I take these actions, what will happen? I will run out of charge. The charge will be finished because I am so what is happening here is that from the low, when it is low and it is moving into, it is wanted to move into a high charge. That means so it will try to travel a distance, and what will happen is that the robot will become idle. So you have to take a truck to fetch it up and bring it. So I don't want this action to happen at all. So that's why I have given it to be -3, this negative reward. I want it to.
You mean to say, like, if it is a low charge, when it is going to recharge in the way it should not search, correct?
Yeah, it is not going to search because
Search. Okay.
So that's why I am giving a negative rewards to it.
But why is that state moving to high when it is saying you should not search?
Yeah, so it means that from low, it has a 0.4 probability and 0.2, right? So what I'm saying that when it moves to high, that means it thinks that it has a high charge. It has a low charge, for example. Now it thinks it has a high charge, and then it moves distance. So it says, I have a high charge. I do not have a low charge. Then it moves the distance a lot. And then what will happen is some point of the robot will stop. So I don't want that action from low charge. If I have to move into high charge, I have to recharge. Right. Without recharge, if it wants to think that it has a high charge, then it will stuck. Right. It will go some distance and it will stop. Then you have to get somebody to pull that robot up because it cannot move. So that's why if I wanted to move from low to high, I should always recharge. This recharge is not there here. So it will think that it has a high charge, and then it will move. So the robot thinks that how it will able to decide. So for example, low charge, it goes here, low, it goes here, low. So see, it thinks that it has a high charge, then it will going a distance, then it will stop. So I want that distance to be less. That's why I think if it is low, then the robot will not go. If it thinks it's a high, then high charge, but it is low, then it will move a lot of distance, and then I have to carry it. Or else you can stop this path at all. So you will not have this path at all. So you can just remove this path if you don't want it.
One question here, in low side and high side, both side, you have a two, you will be in two actions, you are staying in the same state, correct? So which is, one is wait and which is another one is search only, right?
Yeah, one is wait. There are two actions, right? See, there is two actions: search, recharge.
Recharge or wait, okay.
Okay, so this is wait, this is search, and this is recharge. So these are S1, S2. Sorry. These are not states. So these are what? So these are actions: A1, A2, A3. These are actions, and these are state S1 and S2. Now you can write here markup.
One thing, like for example, is robot in low state, and if it sees the policy table, so it will find that there is like 10 for recharge 110, and for wait 111. So now this one, I mean, the second one is the second one is reward, right?
Yeah. So this is the reward.
So either it will
Transition
wait.
probability.
So if it is chooses the reward, then it will wait. Why it will go for recharge in that condition?
Yeah. What you told. So just repeat once what you are saying.
No, I am saying, for example, if robot is in low state, okay. Now it is seeing the policy thing reward. So it will see like for 0.2, there is a chance 0.2, 0.8, 1 and 1 and rewards. So now that other two actions will be rejected. Now the only two actions are there. Either it can go for recharge or either it can wait. So now both will have like reward. For recharge it is 0 reward, and for wait it is 1 reward. So why it will go for recharge? It will wait, right? Simply.
Yeah, but there is a problem here. So you are saying that, see, this is a transition probability is 1. This is a transition probability is 1, right? These two is 1. This is the reward. This is a reward. This is a reward, and this is a reward equal to 0, right? But for example, it is so I. Now it's a condition of exploration and exploitation.
Okay.
Now I will have to, if it is wait, it is exploitation. I am not discovering anything. So I will tell you how it is done. We will see it. Exploitation, and then this is exploration. Now you are correct that it might stays forever. Then it will not recharge because it is exploitation. How it is explore? It is then done with epsilon greedy policy. So it will randomly select a policy at some point of time, and it have to move here, right? Because then it will always exploit. It will not able to recharge. If it is not able to recharge, then it will not able to move distance, right? So with the epsilon greedy policy, a random will shows. Then what will happen with epsilon greedy? It will randomly throw a high probability here, and it has some point. So it is going, for example, 10,000 steps. The robot is waiting. Then the company will say, boss, you have to move because you are just waiting. Then a random, like a number will come. So this is known as epsilon greedy, and it will just jump the state from low to high. Okay. So that is a epsilon greedy, whether to explore or exploit. We will see it. Okay. That is the dilemma.
No, because why I'm telling this, because in wait state also you are giving 1 reward.
Yeah.
So if you are giving 1 reward, means it is thinking this is the correct thing to do. So
Yes.
if next time if battery is dead also, we already gave reward 1, so what better thing he can do?
Yeah, I will explain you this. So what happens is that, for example, I multiply this number with a number known as, so I will say n, there are 10 iterations, 1, 2 to 10. So what is rand 1? So it epsilon value, so there is a epsilon value, lambda. Okay. I will say 1 minus lambda into transition probability plus reward. Very carefully you see, lambda into transition probability plus reward. What will happen here? Lambda value randomly comes to be 0.4. Okay. So what is that? 0.4 into
0.4
1,
plus
0. What
into
is there? It is 0.4. 1 minus 0.4 is 0.6 into 1 plus 1. It is 1.6. I am very happy. It will wait.
okay.
Lambda value is 1. 1 into 1 plus 0. It is how much? 1. Right? 1 minus lambda, 0, plus reward 1. So 1. So it has a reward 1. It has a reward 1. Then in that stage, it randomly decides.
That randomly decides. Okay. Now next time this will get increased.
Yeah.
The recharge one will increase for
Yeah.
this, so it will go for that.
Clear? Okay. We'll discuss this thing. Okay. Okay. So these are, so now we are moving into a very important thing known as Markov decision making process. So Markov decision making process is nothing but what we have learned. It has a state, it has actions, it has a rewards, okay, and it has a so it moves from one state to another. So this is the equation that we saw it, right? So it moves from a state st plus 1 from state s rt plus 1 t, given it is from st to at. So what it means? Don't think of these equations. Intuitive sense. S0, A0, starting S1, A1, R1, S2, A2, R2. This equation is nothing but this. And discount rate is 0 to 1. Now my question is that how do you solve this type of equation? It's a Markov. So whatever we are doing, that thing we defined as to be Markov decision making process. So you have a state, you have an action, you have a reward, yeah, you have this transition, you have the discount state. So it is nothing but this thing what we are discussing for a long time. So A, B, C, D. This is the outcome. I have to go from A to. This is a environment. Again, same thing I told you, right? Environment. So what are the states here? The states are, you can define the states to be SA,
ABCD.
So A is equal to A, B, C, D. Action is left, right, up, down. Reward is 0, 1. Okay. And all the things are covered, right? And the discount rate, okay? So discount rate, again, you have to give 0 or 1. Depends on what I told you, whether you wanted to take average or whether the recent rewards are more important than 1. So if you have this type of environment, these type of things, and this is that thing, right? That it starts from A to B to C plus D. D is the outcome. Now, how will you solve this equation? So this is a lot of things which are coming, right? Now we have defined this state. What we're talking about is a Markov decision making process. We have these type of things. You have a state, you have action, you have a you have that step dynamics. So we are moving from one step to another, and these are the discounts. Very, very important. Agent, what agent knows? Agent knows the state. Agent knows the action, right? Can somebody mute? I'm getting sound. So these are the states. These are the actions. These are the discount rate. These three things we will know, but rewards, actual rewards, we have to calculate. We do not know the rewards. We do not know that one-step dynamics of the environment. These two agent doesn't know. This will be through this Markov decision process, we're able to find out the cumulative rewards and the dynamics of the environment. All right. So why we do not know? Because we know S0, A0, but we do not know R0. Sorry, means R0 was not there. Right?
R1.
R1. Yeah. So these are the known. What are the known and what are the unknown? So you in a environment, this is a RL Markov decision making process, MDP. You give S, you give A, you give the discount rate. Markov decision process will give you what output? The rewards and the one-step dynamics. So it will give you S0, A0. It will give you the optimal. So we'll see what it gives. So S1, A1, R1. So you have to, the MDP will, through solve MDP, we will say that what will be the best path actually. So we have to find out that what is the best path to move from A to B. This Markov, this is the output it will give. So through solving a series of equation. Okay, so it has S2, R2. So all the things it will able to find it out will show. We'll see how it does it. But the output is very clear for MDP. Okay. Now, so we're not going to the, you can just check it. What is the MDP? So we have found, given the formal equation of this thing. So we have already covered it. Okay. So what is the, now, what is the deterministic policy and what is a stochastic policy? Simple thing, we give one state and we give action. So deterministic is nothing but there is no probability involved. So you give a state and the actions are pretty simple, right? And the stochastic policies are, there is a probability. Similar, this is nothing. This is the same thing. So you have state S1, you have S2. So this is from S1 to this is so S1 to S1. So you have a reward, for example, R1 equal to 0. And from S2, you are moving is R1 equal to R1. So R2 is equal to 3. So you wanted to go from S1 to S2. So for S2, R3 equal to 0. And from S2 to S1, what will happen? What is the reward? -1. I don't want to. This is a what? A deterministic policy. Policy is what? Policy is the action. So you go give the state and you move the action. So policy is nothing. People, what is the policy? Policy is what is the best path to move from S1 to S2. So this is a policy. One policy. So policy is either I stay in S1 or I move to S1 to S2. This is a policy. So deterministic. What is the stochastic policy? Same thing. S1, R1 equal to 0. So there is two things. One is similar thing. One is the probability. So probability is preferably 0.8 and the reward. Okay. And what is this? S2. S2 is 0.2 into 3. Here again 0.8 into 0, and here it is 0.2 into minus or minus 1. Anything. So this is a stochastic policy. So we have seen it. Clear, right? Any doubt? So we will see it here. So deterministic policy is recharge plus search. So this is the this is a deterministic policy. So recharge given it is low, right? So this is what recharge given it is low is stochastic is 0.5. Okay. So instead of having a deterministic policy, so these are probability, and always we define it to be weight plus low means what? It is in low state, and I am going a weight, so it is 0.4. So what is this? So for example, a recharge, it is low, so this is that this. Weight it is low means this is weight it is low means this is this thing. So it has probabilities associated with that. So 0.5, this is 0.5. Why I am doing it? Because if it is deterministic without any probability, so these are deterministic. Okay, it is still what is happening is that it cannot explore or exploit. Okay. So search plus low is 0.1. So search plus low is search given low means search given low is this one, I think 0.1. Search high given search high is this one, 0.9. Weight high is this one, 0.1. So in this way I can define the stochastic policies. Okay, so instead of having only a single reward, I have probabilities associated with that, and I can just change any deterministic policies to a stochastic policy. How? I am saying low means recharge and high means search, right? This is a very, very important concept. Low means what is a policy low is recharge. So there are two states, right? One was recharge and one was no. What was that? There was two actions. So this policies is low recharge and so this is a deterministic policy, right? Like policy.
I means collecting garbage basically.
So policy low recharge, policy high search. I can transform this to a stochastic policy because I am using a conditional probabilities. That's it. So this low can have three probabilities based on recharge, weight, and search. Low. So 1, 0, 0. And this high can have three things, three actions, right? Recharge, weight, and search, and based on states. So these are nothing but states, and these are actions. And I am converting a deterministic policy to a stochastic policy. Clear, right? And we'll see why we are doing it. There are some advantage to it. Okay. Now, this is a kind of an example of a grid world. So this is a little bit complex. So what we are doing here is we are moving from this state to the final state, end, say S8. And there can be several ways to reach, and these are the obstacles. So what I can do, and for each of the actions, so actions are what? So how many states? States are S1 to S8, right? Actions are 4, right? Up, down, left, and right. And the rewards are what? Rewards are -1, minus 3, right? Minus 3 and 5, 5. So these are the rewards. So I can form a like a hidden Markov model and find out the states, right? With this. So if I move here, it is -1. Here it is -1. Here it is -3. Why? Because there is an obstacle. Why it is -3 here? Because it's an obstacle. Why it is -3 here? It's an obstacle. Then then it is telling don't take this step. So so I will take this step here, and each of the step I am incrementing -1. So here I get -1, -1, and here I get -1. And why it is 5 here? Because I am giving a more importance because I am reaching a terminal state. So that's why it's 5. So I've defined this grid world, right? Now I can find out the value of each state. Very, very important concept. What I am trying to do, why it is 6? Can anybody tell me why it is 6? -1, -1, -1, -3, -1, -1, -3, 5. With lambda equal to 1. What lambda equal to 1? What is lambda equal to 1? We have, what is
The
lambda?
weight you're
So
assigning.
lambda equal to 1 means the initial, the only the rewards that is important is the current reward. You saw it, right? See. Lambda equal to, lambda equal to, okay, sorry, the lambda equal
Lambda 1 is previous steps are also important, right?
yeah, so we are doing a kind of average. Yes, the previous steps are pretty important. Sorry. Okay, so right now what I am saying is that I then 6. Similarly, I can find out this will be 5, this will be 4, this will be 3, this will be 0. Okay, why this is 0? Because -2. -2, -5, -5 plus 5 is 0. This is 1, this is 2, this is 5. So these are nothing but states. State value. These are the value of the states. Fine. These are the value of the states. So I can find out the value of the states based on the rewards. Okay. Now, so these are the state value function. We have defined it. So these are nothing but I'm giving a name to it, and this is known as state value function. What is state value function? These are states S1, and I assigned a value to it, that is -6. So it is a value of the state. That's why it's a state value function. Yields the expected return if the agent in the state, and then follow the policy for all time steps. So what I am doing, if this guy is here, if my cycle is here, and this is your neighbor's house, this is your neighbor's house, and this is your house. You are taking this path, for example, to reach to their neighbor's house. So that's, and you, for each of the steps you get a reward. You calculate all the rewards, and that value is the state value. These are very, very simple. So this is -6. Again, I start from here. So what I can do, I can take this path, this path, this path, this path, this path, and this path. So the total rewards I multiply. So S5 is nothing but a reward in what? So if I define it to be 0, 1, 2, 3, 4, 5, 6, 7. So revert from 0 to 7. S6 is 0 to 8. What is this reward? S7. State value. What is the state value of S7? So S7 is reward 7. Sorry, this was reward 7. This is reward 7. Okay, sorry, I'm a bit confused. So it is 6. So if you calculate state this to be S0 and this is to be S7, so the state value of 0 is -6. This is a state value function. And what is this? This is a cumulative sum of reward R0 to R R5, right? This is S1, this is S2, this is S3, this is S4, S5, S6, S7, S8. So it is a sum total of R0 to R8. S0 minus 5 is the state value function of state 1. It is a state value function of state 0. It is a state value function of S1. Is the sum total of R1 to R8. A state value of 2. Okay. Sorry, this is 0 now. This should be 6. This should be 6. This should be 5. And this should be 4. So you are able to understand, right, that it is a cumulative rewards of all the states and that it has traversed. Okay, so we now define it. We call a V5 is a state value function for policy pi. What is the policy pi? The value of the state S under the pi. So it is for each of the state S, it yields the expected return if the agent start in state S and then uses the policy to choose the action for all state. Policy, what is policy? Policy people confuse. Policy is nothing but this path you are taking. This is the policy. Okay, so I call it to be pi. And what is V pi? What is V pi? V pi is the value you are getting. So V pi for me it is V. For me it is, for example, V of state 0. So you can think of that 0. So V pi. Pi means the policy I've taken from here to reach to here is V pi S. S means what is the state? S0 is 6. Very, very important. -6. V pi of S1 is -5. So it is for each state. So what is that? It is the E pi. E pi is what? It is the expected return if the agent start from S into. So if it is the expected return if it follows the policy and reach to the end. So that is a state value function and policy pi is the path. Is it clear? So I am making a formal definition. What is GT plus ST plus S1? It is the different states I am getting. So GT ST plus S means is a conditional probability. So if conditional probability means I am saying if I have taken these path, then what would have been happening? Okay. So this is a formal definition. Is it clear?
Yes.
Okay. So I have defined a state value function. Why I am defining it state value function? Anybody intuition? If you do not use a state value function, you will not be able to understand whether the state is better. So if you do not use a state value function, for example, you do not know that if this policy is good, this is a pi policy, or this policy is good, this is pi, for example, this is pi star and this is pi star star. So how will you know whether pi star is better than pi star star is better than pi star star star? How I will able to know it? With the help of state value function. So I know pi star is the total reward that I get, right? So I know this value, right? So I can find out the value of pi star is maybe 0.2. We will see how we can calculate it. Pi star star is 0.8 and pi star 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 is 0.9. So we say pi star 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 is a better policy than pi star and pi star star. If I have the value, then I can calculate whether these policies are greater or less. Okay. So this is over. Yeah. So I will show you up. This is the all the things. So but it is very tedious to then, for example, if there are 100 states, then you have to traverse from start to all the states to get that value function, right? This is very computationally inefficient. There are eight blocks, 1,000 blocks, so 1,000 iterations you have to do, right? You have to, yeah, because you have to traverse the entire path from start to end. See, you have to traverse this one, 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 this one. So 8 steps you need to take. There are 10 lakh steps. So we do not have that computational power. So, so again, I want to highlight is preferably what we can do, we can take a shortcut. So instead of calculating all the value of the states, we calculate the value of this step. It's very easy because we are close to the end state. Calculate the value of this. I derive the value of this one from these three value functions instead of calculating from the top. How I will able to calculate the value of this thing? I know the value of this thing. Okay. So the state value of this means this is S0, this is S1, this is S2, this is S3, this is S4, and this is S5. So state value of S5 is, sorry, we have defined it to be V, right? V of S5 is V of S6. This is this one, plus the reward function of 5. Means 5 to 6. So what is this value? 2 minus 1 equal to 1. So this is 1. A value function of S4 is the value function of S5 plus reward. R4. So it is 1 minus 1 is 0. So if I know these three values only, I can calculate the state value of all these values. I don't have to traverse. So it is computationally less expensive. Clear, right? This is known as Bellman's equation. Previously, before Bellman, you have to do the entire, calculate the entire state of 10,000. If there are 10,000, for example, in 10,000 states, so each we have to traverse from state 0 to 10,000. Right now, we can take the value of S999, S998, and for example, 1000. So S998, S999, and 1000 to calculate the state value of S20, S0 to S997. Is it clear? This is the intuition of Bellman's equation. Is it clear? The intuition is clear, right? So I am saying is the value now, the value of the state is the expected value E pi. Okay. Expected value is the expectation of the value. We are t plus 1 reward plus a lambda into V pi st plus 1 plus. So I am what it is means the immediate reward plus the discounted value that the state follows. So what it does is that, what is this one? This is the discounted value of the state that follows. So I am using a discounted factor plus what is this one? This one is if the agent start in state S and uses the policy to choose the value. So this we have already covered, right? So what I am doing, I am actually doing, if I know the state value of the next two steps, I can find out the state value of these states. So if I know the state value of 8 plus 9 and 10, no. If I know the state value of 10, it is terminal state. I can find out the V. If I know the value, state value of 10, I can find out the state value of 9. I can find out the state value of 8. I can find out the state value of 7. So what it is doing, I take this value and add the reward that is there. I have to take from move to V9 to V10. So this is a formula. Is it clear? So at least we know the intuition. All right. So I take the expected value, multiply with the rewards for the next step, and so multiply with the discounted factor. So I'm not here, what I'm doing, I am totally multiplying. So 2 minus 1 equal to 1. So here, instead of multiplying totally with this, I have a what? I have a discounted factor. So what I do is that I multiply, say the discounted factor is maybe 0.1. So instead of doing vanilla 2 minus 1 equal to 1, I do is 2 into 0.1 plus, so 1.2. So instead of 1, we have 1.2. Why I am multiplying with the discounted factor? Can anybody tell me why I am just using a discounted value? Can anybody tell? What is the intuition? Why I am using a discounted value? Can anybody tell why we are using a discounted value? Very, very simple. I am saying these two, I am multiple. So I am saying it is discounted. Means what? So see, the value of any state is -1 is equal to the immediate. So what I am doing? So I am like seeing the immediate rewards, and I am multiplying the previous value into some discounted factor and adding a reward, adding a current reward. So why I am using this discounted factor is because we are saying that so for example, something happens, so take this value as today's state value, okay, and this is tomorrow's state value. And these are historical observations, so you know it. Maybe tomorrow's state value, you know. Now I am saying that that today's value is not totally dependent on the previous value. There is some discounted factor, because as a time has passed, it might happen that those values might get changed also. So that's why I am adding a discounted factors to decrease this importance. That is the intuition of this lambda.
Okay, so just to so the latest output, latest reward, we want to cumulative reward. We want to decrease the dependency of previous.
Yes,
Reward.
we saw that, right? The discounted factor. That's a reason. So Bellman's equation is one of them. This is a backbone of reinforcement learning. Now I have to solve this V5.
One question, when you're saying lambda, right? Lambda is the weight we assign, saying whether it is dependent on my recent rewards or previous rewards. But then your discounted
No.
like
this is separate. This rewards is a different, and this is a state is different. So this is a discounted value of the state, and that lambda is a discounted value of the rewards. So you can add that. So for example, if you can add, this is I think this is not lambda, this is gamma, right? So what I am saying is that you can term this equation to be like this way also. V pi s into E pi into lambda into RT plus 1. See this. Plus gamma into V pi st plus 1 given st equal to s. So there are two parameter. One is gamma and one is lambda. This
gamma is the discount rate.
Yeah, basically. Discounted state for the state, and lambda is a discounted for the rewards.
Okay.
As I have considered the lambda to be 1, that's why I am taking the rewards. This current reward is only matter. The other rewards doesn't matter. So you can also add that. We'll see that. Okay. So this is a Bellman's equation. So Bellman equation is a way we can solve by Markov's decision-making process. And the entire reinforcement learning literature is to solve this equation. There are different ways to solve it. If you know this equation, your reinforcement learning is covered. Now it depends on the techniques. Okay. Now, so now there is that with this V pi, so you can understand, if I know the V pi means values of each state, I can find out the policy. Policy is nothing but the path I take from starting point to end point. So with two policies, means either I take this path or preferably, what is that path? I take something, this policy is looking from where it has started. Okay. Yeah, or the policy has started from here to here to here to here. There are two policies. I can compare the policy. This is pi and this is pi dot pi hash. It depends on which policy's value is greater. So that is a better policy. By state value function, we calculate the value of each of this block, each of the state, and we sum total all the states with the rewards to get the value. So how will you do it? With the Bellman's equation. Bellman's equation will give you these values, right? It will give you the state value. Now, if you get the state value, it is very easy to calculate the policy. Policy is nothing but the sum total of the state values. Okay. Now I am saying is that if a policy has a greater cumulative state value than a policy, then I will say this policy is better. Why this policy is better? Because 2 is greater than -6, 3 is greater than -5, 4 is greater than -4, 5 is greater than 3, and also you can say this policy is better. Because the value of the states are greater. Okay. Now, it can happen that both of the policies can be optimal also. So you can say that the both of the policies can be optimal also. Okay, that can also happen, that both the policies are optimal. Okay, why it is optimal? 3 minus 2. Minus 3 minus 3. Okay. Oh. Why it is optimal? Let's see it. This is what? This is this policy. So this is -1, -1, -1, -1, and +5. All right. -1, -1, -1, -1, and +5. So it is how much? It is 4, right? If I wanted to go here, -1, 1, 2, 3, 4, and it is 1. So this is 1. And for example, I wanted to go from here, and or I wanted to go from here, and so what is that reward? So here reward is -1, -3,
minus
here
but +5.
+5, minus, yeah, so
No,
3,
but there is
4.
no way.
Yeah, from here to here, right? So I am taking this policy first. This can be 1. So it is -4 plus 5 plus 4, 1.
1.
That means this policy, if you wanted to travel from here to here, and this policy, if you wanted to travel from here to here, either you take this path or either you take this path. Both are optimal. So I'm saying both are optimal policies.
How it is optimal?
This is one path. Another path you can take this one also, and see. When I'm wanted to stress that both the policies can be optimal if the value function is equal. Okay, that's why your pi both the policies are actually optimal here. So that is a. So from here we will see that definition. So what is the definition for optimal policy is very, very important. If the policy prime is greater than prime, yeah, if a policy prime is greater than a policy if and only if its value of all the states is greater than value for this one. It's often possible to find policies that cannot be compared. If the values of those policies are greater, then I will say that the policy prime is better than the other policy. So optimal policy pi star satisfied pi star is greater than pi for all values. Optimal policy is guaranteed to exist but may not be unique. Optimal state value function is denoted by V5. So you can say that it might happen that 2 or 3 policies can also be optimal. So it's not that we'll get a one kind of a solutions, but it can happen that it can have multiple optimal solutions. But in order to say that a policy is to compare the policy, we have to calculate the value of the state and the total value of the state, and that can be done by Bellman's equation. So you use a Bellman's equation to solve this value. You use a Bellman's equation to solve this value, and then you compare it. So this is a grid world, for example. So you wanted to calculate A to B, C, D. So you take this path. This is pi 1. So you take the pi 1 should have, and this is a policy should have a value associated with the policy. So this is, for example, this value is for all the states from A to D. And this is calculated to Bellman's equation. Then again, you take one policy, you take A, B, C, D. And for example, you take a path like A to D. This is pi 2. And then the value is from A to D. Then you compare the value. So this value comes to be 0.2 and this value comes to be 0.8. Now you say that the policy 2 is better than policy 1. And this you find out, we'll see how we'll able to find out the value. Okay, so we saw intuitive sense how to calculate the value. But there are other ways, because if you calculate the value, if we get the value of each of the states, then it is very easy to calculate the policy value. If you know the value of the state, you just add the value to get the policy. So you have to first find out the values of the states. And that can be done through Bellman's equation. Okay. Now, this is again a state value function is something this. But there is a coin that in order to calculate the value and get the policy, it will take some time. Okay, so we wanted to make it a little bit faster. So we will use the Bellman's equation also to get a action value function for the policy. Instead of having a state value, see, the policy can be find out by 2 ways that we will discuss. I will show you. This is what? This is a through state value function that we saw it, state value. So you find out the value of state and then find out the which of the policies. See, then you say that which of the policies is optimal. Okay. Like you find out the value for each of the state, it yields the expected return if the grants the states in ST and then chooses the policy. So it's a state value means you get the value of all the blocks that we saw it, and then you find out a better policy. Okay. Same thing we can do, find out the policy by picking the action value function. The action value function, we will see it is same as state value, but you have action associated with that. So I will show you in later slide what is the difference between a state value and action value. Same Bellman's equation can be solved through the action value also. So here it is only state, here we are taking action. Action means right. So instead of saying, so state value is intuitive sense is state value is S A B C D. The state value is 0.1, SB is 0.2, state value is 0.3, and for example, state value is 0.4. This is a state value. From there, you can find out the policies, right, by adding the state value. Action value are like this. You have, I will show you, have 4 block, right? This for each of the states. So if you go up, what is the value? If you go left, right, what is the value? You go left, what is the value? You go down, what is the value? So there are 4 values associated with that. So we write SA equal to 0.4 for state value. For action value, we take SA. If I say, for example, up, so SA up is 0.2, SA down is 0.3, SA left is 0.2, 0.5, and SA right is 0.3. Understood? Then you have 4 functions for each of the state. Okay, then that's a action value, and this is a state value. Clear, right? So we'll see it in the later slides. So the state value yields the expected returns of 4. So this is a simple thing. This is only 4 I am giving for the state. Action value would be what? Action value function yields the expected return if the agent start in state and takes the action and then follows the policy. This is the part. And what is the state value? State value yields the expected return if the agent starts in the state and then follows. There is no action involved. So state value is just 4, right? Here it is, if you take a, like for each of the actions, for example, if you have actions left, what is the value? Here up, what is the value? It has a 4 values, actions, state value actions. And state value is contains only the state that is there. So that's the difference. Is it clear? Or any doubt is here? Okay. So for each state and value, the action value function yields the expected return if the agent starts in the state and takes the action. Similarly, same thing. Instead of having a state value, we have right now an action value. You start from 0. 0 means what? I take a up and I start with function 0. And then I move here, here. Okay, and then what is the reward for action down? So what is the reward for action down? So just hold on for a minute. Yeah. So what was it? Yeah. So for example, I take a downward action. Okay. So this is -1. I take a upward action. This is -1. I take a right. This is -1. I take another right. This is -1. I take it down. This is -1. I take it down. This is 5. So it is 0. Reward from the following policy is 0. Right? If I take it down, what will be the action value if I take a right? Somebody tell me. -1, -1, 3. -1, 2. -3 plus 5 is 2. What is the action value of this state? 0. Because you cannot move, right? And this is also 0. Is it clear? So now we can have each of them, each of the states. Okay. So we'll see it. So this is the reward for action up. Okay. Action up. Action up is what? This is -1. This is -1. This is -1. This is -1. This is 5. So this is 1. So in this way, I told you, right? This is 2. I draw it. So this can be, I can fill it up, the entire chart by this. And this I can fill it up. So you know that, right? So in this way you can fill all the things. We show 2, you know that how, right? This is 3, how? -1, -1, 2, 5 plus 5 minus 2 is 3. So in this way you can fill it up for each of these blocks. You will understand. This is 5. 5. This is 1. I think 1 means -3 and okay, minus up means -3 -4. 5 minus 4 is 1. So just the concept is that you will remember that I wanted to, if I start from this position, what are the steps I should take till I go to the end? So this is the part. So if I take a left, I go up, 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 up here. So this is 1. Why? This is -1, -1, 2, -5, -6, 6 minus 5,
One.
-4, -6 minus 5 is 1. So there is no negative. Just take a mod of it.
So this thing's called action value, correct?
Yeah, state action value, not action value. State
State
yeah, state value is only 1. Okay, but action,
okay, state.
yeah, action value is if you take with associated with that with action, what is the value? Okay, now you have, this is the comparison between a state value and an action value. Similar thing, same thing. So you can find out the policy through state value or an action value. Okay, you can find out the value of state and then decide which policy is greater, or you can directly find out the policy with the help of action. So it is quicker. This is a little bit faster. So this is over. Now this is the value iterations that we are talking about. So so I think I will like to explain you these value iterations in a more like you this is an algorithm, and we will try to see the examples to see that what is the difference between a value iterations and policy iterations. Just wait. How much time we have? I think time. So what is the value iteration? We saw it, just an algorithm. This is a pseudo code. So we start with MDP with a very small positive number or 0. The output policy is pi star. Begin with some initial guess. It can be 0 or it can be random number. Stop if the value doesn't change. I told you, right? If the if you do a grid world and see that for example in this one it is pi 200 and this is policy pi 201. These two are pretty same, so we will not iterate further. We initializes the value to be yeah, so it is if the change is close to 0, we will not iterate. For E, for S means we loop over all the state. We saw that. So we are taking the value of that state and we are taking the max part of it. We'll see it. So we will do the value function and see that what is the maximum value and we take it. So we'll implement it in programming as well as with this. So just hold in for a bit. This is just an algorithm. check how much the value has changed, and update the policy with the value function. So this is the value iterations we are doing. Okay, so we will see it. Okay, we will see it in the later on. So this is just a pseudo code of policy iteration is same as value, but we have the actions here instead of value. We have seen it, and we stop when we do not have an action. See, it is quicker, right? So we are finding out the value, and we from that value we are taking the max value and all. So this is intuition is what I told you, right? That I told you A to your move wanted to move. This is a value iterations. So you have A, B, C, D. So you take all the steps. So A to A to B, A to C, A to D, B to B, B to C, B to D, C to D. It can anything, right? C to D, then C to A, C to B, then your C to B, and then so you have those values associated with that 0.1, 0.3, 0.4 here. So we take a maximum of from A. So all the state I take the maximum value. So I say A to B has my maximum value, right? So it is maximum of all the values I get. So I say A to B it will go because it has a maximum value. Then it sees B to all the things, B to C, B to D, B to C, which is a maximum value. So it sees that B to D is a maximum value, so it goes. So this is that what I'm talking about. The maximum it takes and try to, these are value iterations. We will see it in greater detail in iterative policy is again same, but here we are not iterating values, we are have a state action. So what I'm saying is that instead of having this a single value, we have this bracket, right? And we told you this is a policy iteration. So we have actions and action value, and instead of updating the value with the policy, I am updating the policy itself. So this is the iterative policy iterations. Okay, this is the part. Okay, now we have a what is policy improvement. So this policy evaluation and policy improvement are same. What is, I start with a random policy pi. I do a value, find out the value function. Okay, I found out the action value function q pi, and I find out whether this policy is good or bad. So this is a policy improvement. So policy improvement and policy evaluation goes together. Then I again takes the next policy. So this iterates. I take a policy, I found out the value function, I found out the action value function q pi, and then I decide that whether the new policy that I get is a better policy or my previous policy was better. If how I can find out, by if the value is greater, right? I told you pi 1 is 0.3, if pi 2 is 0.1, my pi 1 is a greater policy. This loop will end. If pi 1 is then it compares pi 3 with again with pi 3, it is 0.5, then the policy pi 1 replaced by pi 3, then check policy pi 3 with pi 4. So it compares each of these policies and find out that which is the best. So policy evaluation and policy improvement happens side by side. right? Until we find out that there is no significant improvement, and two policies can have a single optimized policies can be, I told you that there can be two policies that might be optimal. So policy improvement is simple, that obtain the action value pair and find out that which is a better policy. Is it clear? We find out the action value and find out that which is a better policy. Okay. So this is a very, very important thing. Okay. So I will show you how this policy evaluation occurs in a intuitive sense. Okay. So this is one of the very beautifully iterated this thing. So value iterations. So value iterations, what is the algorithm? It starts with a random value Vs. It for each state QSA means, what is QSA? I am taking for each state, I am finding out that if I take action A, so what is the value? We'll see it. Since Vs equal to max QSA, update the value to QSA. If the policy is optimal, it is no, I continue to loop, and if it is optimal, then I stop. So what I am saying here is, I start with a random policy and we look for a new improvement value function in an iterative function, and we will end it. So you will able to understand this in a very clear way when we will do the algorithm. So this is a grid. So let's say that we are in state A. Our goal is to go to state C. Without visiting state B, we have two actions. One is 0, means left, right, and one is up, down. Can you find out the optimal policy here? Okay. See how we can find out the optimal policies. So for state A, we have a value 0. Initially, everything is 0. Okay. Now, I do is, for each state, means S, this is a Q table. So we are trying to solve a Bellman's equation with the help of Q table. So this is state S. This is the action I take, that is up, down, left, and right. New state will come with a transition probability, with a reward probability. Nothing. This is S dash transition probability associated with that. So S0 to S1 with transition probability P1 with reward R1. This is the transition. Then again S2 and all. So why it is what is 0? 0 means what? 0 means, they have said 0 means left or right, and 1 means up and down. So this is left and right, and this is up and down. Okay. Now, and these transition probabilities are there. Okay. And you can draw a Markov's chain also. Now, how will I calculate the QSA? Okay, so Q function is, what is Q function? Q function tells you the value of the action in each state. So it says whether we should take a left or right or up and down. Okay. So what is the equation? This is what? This is the transition probability, similarly, into reward probability plus gamma plus value into next function. Can you tell me what is this equation? We have done with the equation. What is the equation? Transition probability into reward probability into plus gamma into the value of next function. Can anybody tell what is this?
This is to calculate state value,
This is
state value
nothing.
action.
This is nothing. This is nothing but the Bellman's equation. It is nothing but a Bellman's equation. So I'm trying to solve the MDP. Very, very important. So transition probability is nothing but, what is a transition probability here? Transition probability is nothing but E pi. Okay. Into I am multiplying the, okay, where is that? This is, sorry, this is, yeah, transition probability into, see, this is a Bellman's equation. So this is transition probability. This is the revert probability, discount factor into the value of the next state. So this is nothing but we're trying to form the Bellman's equation. So Bellman's equation is nothing but, this is a transition probability, that is E pi, E expected value into the revert probability plus gamma into next state value. Same, this is a Bellman's equation. So let's do it for A0. So A, it is up. Zero means what? Zero means, I forgot.
Right, left.
Left and right. So either I cannot see, I cannot go to left, I can go to right only. Okay. So left I can take it. It is the state doesn't change. You go left, it doesn't change. You go right, it changes to B. Very, very important. Okay. And A0 to C. What is A0 to C? There is a A0 to C. Okay. So A0 to C. A0 to C. Okay. So 0 means left and right, and 1 is up and down. So left is left is A. I take a right. I go B. Okay, then it is saying that A0 to C. Okay, A0 to C. A0 means left and right.
I think via B or what?
I think it should be, I think it is, I think it is, oh, it has taken all the combinations. So A1 it's C, A1 it can be up and down. Okay, it can be up and down. So A1 is there, is C, A1 is B also. So A1, okay, it has not, it has, it is,
Okay. It is like
it is not,
combinations.
yeah.
All
So what it
combinations.
has done is that it is taking all the combinations. So
Oh, then we can see there is a
yeah,
zero,
now we
zero
can
is there.
see it actually. So what is that? Then state is there, and these are the transition probabilities, and this is the revert probability. Okay, so each of these state can have three actions. That's why it has a three actions. Three actions are, it can go this way, this way, this way. That's why each of the state has three actions: A0, 0, 0. So if it goes,
Actions are left, right only, 0 or 1, but it can be three state. Either it can be stay in A, either it can go B, and either it can go C.
yeah, that's why. So it can,
Okay.
that's a Bellman's, that is a hidden Markov, right? That is a Markov's chain. Yes, it can go to state A.
Okay.
It can go to, so actually if you can draw it will be better. So if you can draw it, then you will see it. If it goes into it, it can stay in state A, it can go to state B, and it can go to state C. Also it is for one, it can go to stay in state A, state B, and state C. So so that's a thing, right? So so then it has taken all the values, and it is trying to say that what is a transition probability and what is a revert probability. So this is the equation. So A0 is what? PAA, right? So it is 0.1 into 0 plus 0. Why it is 0.1? It is transition probability 0.1 plus gamma. Okay, so it is 0.1 into what? RAA. So what is RAA? RAA is a reward at state A. So 0 plus lambda value is 1. Kintu what is a value, initial value of A? Everything is 0 here, ABC. So it is 0. Similarly, PAB is what? 0.4 into what? 0 plus 0, 0.4 into minus 0.0 into minus 1, because it has a reward minus 1. Minus 1 plus lambda into value of B. So everything is 0 here. Okay, because value of this value is 0, because initial everything is 0. This value is 0. This value is 0. So this doesn't affect. So we multiply only with transition probability with the reward probability. Minus 1 into 0, minus 4 into minus 1, minus 3 into 1. See, that have done. So I multiply the transition probability into reward probability. Okay. That we have seen it actually. Okay. So now it gives A0 is 0.1. Okay. Similarly, I do it for A1. So it is 0.3. Okay. Now what is a state value? So now I am converting that action into state. So A0, A1, 0.3. So what I will take? I take a max of it. I am not concerned with the action because it's a state value. So A value would be 0.3. So what I mean to do is A1 0.3 means if I take a left and right, up and down, okay, I can go to C. I can go to C. A is, I can go down, so it can be down. I can go to C. That's why it has been given this thing. Okay. So this is clear, right? So from the Q table, I say that A1 is 0.3. Okay. Now I find
one.
Yeah. So I said if I take A1, this is A action 1, that is down or up, I can go into that value 0.3. So A's value is
Okay. For A left right, it is minus.
minus 1. So this is less. So this I will not take.
Left right, but we can go to right into B.
Yeah,
right?
yeah. So it is up and down. So you have to go down because up that 0.1 is up or down. So I'm saying either we can take up and down, but intuitively it is down only. So the value is 0.3. Because up you cannot do, right?
No, up we can't do, but left right we can do, right?
But right we can do, but the value is less here, 0.1.
Okay,
That's why I am not taking. So I am taking this 0.3. Right.
So our final goal is to reach to C, right?
To reach to C, yes.
Okay. So for that matter, mathematically we have proved like the 0.3 is best.
0.3. Now we compute the Q value of all the action pair. So likewise, we again do it for B. Yes, a B1 is, for example, 0. B is minus 0.8, for example. B1 is minus 0.2, which is higher. 0.2 is higher. That's why 0.2 here comes. Then C is, for example, 0.4 and C1 is 0.5. I'm just giving examples. So I take max out of it, then it becomes C 0.5.
So I have, but C it is like wherever it goes for it, both are same only. So 0.5 easily, right?
Yeah, so you can think of as C0 and 1. So C is, but
I mean, if C is our goal, so if we go to B or A, doesn't matter for us.
Yeah, but actually I want,
fine.
So I want to, because it's mathematically you have to do, right? So you calculate all the possible combinations and you will see that, it doesn't matter actually. So whatever value it comes up, because it's a terminal state, doesn't matter. Okay. Now, next we repeat this thing for several iterations. This is what episode 1. So I again take episode, this is for episode 1. Okay. Now I take this to be for episode 2. Repeat. Then I take to be episode 3. See, the value are getting changed, right? But if you see, the values for episode 2 and episode 3 are not changed much. But for episode 0 and 1, it has changed a little bit. So I will not iterate after episode 3.
And
Because,
also state value of A means A value is higher only all the time.
yeah,
Which
it is
means we
higher.
in
So see,
first
this,
time only we find optimal thing.
yeah, it might happen or it might not happen. Yeah, for it,
Okay.
it is happening because this difference is very, very less for each of
Very less, and only three states we have. That's why
3 states is that. So simple. So, but A's value, yeah, A's value is not changing. So we'll stop. So now my state value, my value function is there for each of the state. Okay. Now I convert this state value to action value. I know it. Okay. I convert this state value to action value and say for A00, 0. So when we compute the Q function, so what I say from like from this thing, I convert back to action value. So say A0, it was for the final state, it was 0.53. A1, it was 0.98, and then B0 was 0.2, B1 was 0.3, C0 was 0.2, and C1 was 0.1. So tell me what action it should take, because from the state value, optimal value function, we got it. Now we compute the Q function with our optimal values. So we convert these values to, for example, Q function to find out the action value. So for state S1, for action 01, what is the value? So these are the final values you get. Right. Because you know how to get this value, right? We know it from here. It is coming. Okay. This table is there. So this is a, you know that this iterates. So we, from the state action value, we find out the state value. Okay. And then after the final state value is done, we wanted to convert back to state action value. Okay. So what is the final this thing? So you have, what is the highest value for A to 1? So this is highest. Okay. This is highest. Okay. So A1 I take. So what is A1 is down. Okay.
down.
Now B1 has a less value than A1. Okay. So what I am saying, from A1, if I take this is C, right? And this is A, this is B. So if I take down, I move to C. I don't require B. B is not required. So I directly move up into C. So maximum value is 1. So we perform action 1 to reach to state C without state B. So this is the value iterations. Is it clear?
Yes, it is clear. So, for example, if we are in state A, so now it needs to see two ways are there, 0 and 1. Action can be done, and according to their value, we will move from A to C state. Okay.
Yeah.
For example, if we reach to B state, then we need to see the in table what are the actions can be taken from the B. Correct?
Yeah.
Okay.
So this is the internal. It's easy. Okay. So there is another type of function, that is policy iteration. Unlike value iteration, the policy iteration starts from random policies. So we don't calculate the value, we calculate the policy directly. Okay, if the value function is not optimal, new policy is there. So we start with a random policy, calculate the value function of the policy. If the VS is optimal, we stop, else we find out the improved policy. Instead of having the value, we directly go into the policy. Policy means there should be actions involved. So let's this is very easy. So we start with a random policy. So A's value is 0. These are what action. A0, B1. We are not concerned about the value of ABC. Now no action. A0, B1 and C0 are the random actions I take. Okay, and I take to find out the value function of the actions. You remember that value policy, we find out the value, then actions. Okay, that is a value iteration. Policy iteration, we take the action and then calculate the value. It's just a reverse. So for each of the actions, we calculate the value. So what is the value here? A 0.3, B minus 0.2 and C 0.5. So A has a we have a new value function from a randomized initial policy. So this policy is 0, 1, 1. We have a table where we get the value of A, B and C. Now we calculate the actions associated with this value. Okay. Now we will see this 0, 1, 0, that action we have taken, that will change. We start with 0, 1, 0 action. We calculate the value associated with the action, and we will see that what is the new action value. So now it is 0, 1, 1. So with this table, I get a action maybe of 0, 1, 1. That gives the highest value. We keeps on iterating the value and get the new action A1, B0, C0. Now,
can you little bit up go up? What was the previous action? Okay, A0 only.
A0,
okay,
B1, C0. So you, based on this action, you can find out the value. We saw that in the previous slide. So if you have this action, you can find out the value, taking the maximum. Okay.
Okay.
So what I'm doing is that you have the action first. So there the value was first. Remember that. In value iteration, what we were doing is that we start with the set of values.
Okay.
Here in policy iteration, this is a value iteration. So I will draw it.
So
little bit, yeah. Let me complete it and then we will.
I will compare. Yeah.
So right now, what I've done is that you have calculated the value. Okay, we have calculated the actions. Okay, based on that, we calculated the value. Okay, and then we use a Q function to transform this action, the value to the action. We saw that the recent actions are A0, A1, and C1. So now we compare the old action and the new actions and see that whether, so based on the value, so we see that this action has changed. So just now this action is 0, 1, 1, 0, 1, 1. So instead of having a 0, 1, 0, we have a 0, 1, 1 actions, and this repeat. So pseudocode is what? We initialize a random policy with the number of iterations. We find out the Q value. Okay. Find out the maximum pair of Q values to find out the new policy. If it is better than the existing policy or not. If it is better, replace the policy and keep iterating. So let me draw it. What is the value function and what is the policy function? Value update, policy update. Value update, if it is value update, so it starts with this one. So it starts with preferably a random value 0, 0, 0 for A, B, and C. Policy update is something very different. Policy update is nothing but left. Okay. Random policy. This is left and this is down. Sorry. This is I am saying A, B, and C. So I move left, and B to C. I move this one, B to C, and C is I stay. Maybe I stay here only. So C is I don't want it to move. I wanted to stay here. So I start with random policy, random values. So A 0, B 0, and C 0. Concept is same. A left, A right, value 0. B down,
1.
maybe 1. Okay. And C, if you think C, C, I am not doing any action. So for inactions also you can find maybe 3. You are not doing any action here, inactions or something like that, or write down, and maybe for in order to see that, or else
If you want to stay there, then you can give 1, right? So down it means nothing is there. So it will
yeah,
stay in
down. So
C.
you can see down. Sorry, it can be down. So you give 1. Okay. Now this is the value iteration. This is the policy iterations. Or else I define. I start with the random policy. Now I find out through hidden Markov. First of all, I draw this ABC again, ABC, and I draw that hidden Markov model again. So A to B, A to A, B to B, B to A, okay. Then B to C, C to C, A to C, okay, and A to C to A or C to B is not possible. Or else if you wanted to give, you can also give some negative reverse. It depends on you. Now, right now with this equation, and this equation is universally followed for all of them, for policy and value. Now I do the transition table. So transition table will contain what? The current state ST
plus 1.
Yeah, this is the what? The transition
Correction.
probabilities.
Transition
Transition probabilities. This is the
values.
And I give it. So from A to, okay, there should be another thing.
Now one more thing will be there.
Action.
Action.
Yeah, action. So I say A to A. Again, action 1, transition probability something, reward probability something, like 0.1. So from A to again B, all the cases, A to A, A to A, A to B, and A to C. Okay, and for action, maybe I take all the combinations 0, 0, 0, and 1, 1, 1. So from there, what I get is that I will solve the, and then I will use a Bellman's equation to solve. It's not Bellman's equation. This is a, I will use this. Yeah, I will use a Bellman's equation.
Q of A of 0.
Yeah.
F1.
So this is what? This is V of, so V of S. So this so this is iteration 1. So V of 1 is the total S. So you define it to be episodes. Maybe it is first episode. So episode 1, V of episode 1, you get is what? The transition probability into the reward probability plus lambda into what? The current state ST plus
1.
Current state
ST,
and I think the next is that it is the
gamma. It was a gamma.
No,
Gamma is
ST plus ST plus 1. I think That was there, right? ST plus 1 is a next state. So I have to take the current state and the value of the next state, right? I think I'm not wrong. Just hold on. What is that? So the formula is what? Formula is, for example, yeah, gamma into the, oh, okay, gamma into the value of the next state only. Sorry, gamma into value of the next state. So it should be it should be ST plus 1. I think it's ST plus 1. Okay, next it is if it, yeah, so it is a value of ST is equal to transition probability to move to the next state into reward probability I get to go to the next state plus lambda, the discount like the lambda into ST plus 1. It is the value of the next state. So in this way, I calculate the value of A, B, and C by taking the maximum, you know that. So maybe the value is 0.4, 0.3, 0.2. Then I iterate, and I stop when A, B, and C's value was not changing. So with this A, B, and C value, I can find out the optimal action. So I know that A0 from A0 is, for example, 0.2, A1 is 0.3, A2 is 0.5. I take A2 because it gives me the highest action. Okay, so I say that, and B again, B0, B1, B2. So all the B's value is less than A. So I will not travel to B, I travel to A to C. This is a value update. Policy update is exactly same, but I am directly starting with a random policy. R0, 1, and 2. What I do is that, again, make a transition table and find out the value of ABC. Okay, this is a Q function. ABC again, 1.2, 1.3, 1.4. And I see that what is the best policy to move from A to C. So I say that again, A to C is greater. So my then I say the optimal policy of 0.011 is 001. Because if you take 011, it is not an optimal policy. 001 is an optimal policy based on the value. So this is a difference between the value and policy update. Is it clear? Difference between the value and policy update is I start with value in value function and try to see the optimal policy by the use of value. Okay. In policy iteration, I start with a random policy that is 011. I find out the value of the state, and from value of the state, I find out the optimal policy. Same thing. Only difference between value and policy update is that I start with a random value. Here I start with a random policy. And then the Q function is same, everything is same. Then I find out the state which has a highest value and what is the associate actions associated with this state. And I change this in policies. That's a thing. So I want to stop here. To next class, we will be writing a programming in Python to solve this. If there is any doubt, just ask me. This is a little bit of confusing, but still everything is same. See, I start with this is value, a random value. I find out the QSA, that is the action pair, maximum value of QSA, and we repeat the state until the value function is less. So QSA is the Q function. Okay. Here in value update, we also do the same thing. In policy iterations. Policy iterations, what we do, we start with a random policy. We found out the value function for the random policy to check if it is known as policy evaluation. We try to see whether this is optimal or not, and we repeat the steps. So we do a policy evaluation plus improvement. Okay, so this is a part. So what I do is that we start with the random policy. We see that whether this random policy is good for us or not. Okay, so with the help of the state, right? And I change the value of the states, the value of the state, and see that if the new policies that is coming from the changed value is better than this policy or not. Okay, so if it is better, then I continue, else it stop. Simple. I start with a random policy, I number of iterations, I find out the Q value. Okay, so same thing, I find out the Q value of the function. If the new policy is better than the old policy, then I update the random policy with the new policy. Else I move out. And how I evaluate the policy is good or not? With the help of Q function. Whether I need to know whether the value is great or the policy is great, Q function does the work for me. Why? Because this value equation that we see it, we can transform it to the Q function also. So we see that, right? So this is a part. Value is here. This is a value update, same equation. And this is the policy update. So because the Bellman's equation can be used for value as well as policy. We start with a random value, then derive the policy from the random value function and see whether the policy is good or bad. We start with a random policy, use the value function for that policy and see that whether the value function is good or not. And if it is good, then we derive the random policy from the value and check it. So this is the crux of the matter. Any question?